we've just noticed something strange that pops up in almost every image of the early universe. Little red dots. They are scattered across the earliest reaches of the universe, some of the oldest objects we've ever observed. Everywhere we turn, there they are. And yet, no one knows exactly what it is we're looking at. And the more we learn about them, the stranger they become. These little red dots don't fit any of our existing models of star, galaxy, or black hole formation. Something this ancient should be small, chaotic, slowly building up mass over time. Instead, they're incredibly dense, dazzlingly bright, and far more massive than we'd expect. So, what are they? Some now think these little red dots might be a new cosmic body entirely. Part star, part black hole. But is that even possible? And what would their existence mean for our understanding of how the early universe formed? I'm Alex McColgan and you're watching Astrum. Join me today as we unpack why these little red dots defy explanation, examine the latest theories about what they are, and discover why they could be the missing piece in one of astrophysics' biggest mysteries, the formation of supermassive black holes. Since the James Webb Space Telescope launched on the 25th of December 2021, it has completed over 32,000 hours of observation and sent back more than 600 terabytes of data. That's enough to fill the memory of more than 2,000 phones. And within these tens of thousands of images, one type of object keeps cropping up. These dots were first seen in the Eiger and Fresco surveys, observational studies hunting for galaxies at extreme distances. Their purpose was to examine the very beginnings of our universe, some 500 million years to 1 billion years following the Big Bang. As James Webb scanned the skies, nearly every photo it sent back of this era revealed the same strange object, little red dots scattered across the early cosmos. By 600 million years after the Big Bang, it seems our universe was filled with them. But 1.5 billion years later, they disappeared completely. This instantly made them one of the biggest mysteries in the universe. But what do we know about them so far? First up, they are very compact, usually no more than 500 light years across, which is about 200 times smaller than our own galaxy. They burn unusually bright for their size and are very red, which is why they've evaded detection for so long. Until now, we literally had no way to see them. Hubble was calibrated for shorter wavelengths than we are seeing from these objects, and other telescopes didn't have the power needed to look that far back in time. James Webb is the only telescope specifically designed to see the mid-infrared wavelengths characteristic of these little red dots. By combining data from its near-infrared camera and mid-infrared instrument, astronomers caught a glimpse of these ancient objects for the first time, though their properties wouldn't be described and categorized until March 2024 in a breakthrough paper written by Jorit Matti from the Institute of Science and Technology, Austria. Now, as many of you will already know, the older the object we are looking at, the redder it appears to us. It's classic redshift in action. Since the universe is expanding, the fabric of space and all the light passing through it gets stretched too. The wavelengths of light get physically elongated on their journey, and the longer they travel, the more they get stretched, so the redder they look. But when astronomers broke the little red dots light apart into a spectrum, they found the redness runs deeper than that. The redshift alone couldn't account for just how red they appeared. The researchers' first instinct was that this may be caused by dust. Dust particles are much better at scattering shorter, bluer wavelengths of light than longer, redder ones, making the object appear red. The same thing that happens to sunlight hitting Earth's atmosphere at sunset, which is why the sun looks red in the evening. But to be sure, the scientists enlisted the help of another instrument, the near-infrared spectrograph, and what they saw just confused them even more. The near spec aboard the James Webb takes the light from a distant object and splits it into its component wavelengths. Different elements absorb light at specific wavelengths, leaving gaps in the spectrum like a fingerprint. So, if there is something like a dust cloud between the telescope and the light source, not all the light will make it to the instrument. By looking at which wavelengths are missing from the reading, we can figure out what the dust cloud is made of. Researchers noticed that these little red dots were emitting a lot of blue and UV light, lots of red and infrared light, but not much in the middle. The result is a highly unusual V-shaped spectral energy distribution. Nothing we knew of in the distant universe was associated with such a spectral signature. But we did get one clue. At 364.6 nanometers, the spectrum shoots up sharply. For some reason, light with wavelengths shorter than this was being readily absorbed, and longer wavelength light was just passing through unobstructed. This is a well-known signature, and it even has its own name, a Balmer break. And when we see this in a galaxy, there's only one explanation for it: young, hot stars. Lots of them. Scientists thought they had it. Little red dots must be early starburst galaxies. It certainly would have been a very elegant solution, but that's rarely how these things go. So, theory number one is starburst galaxies. Now, this starburst galaxy theory had a lot going for it. Hot, young stars are rich in hydrogen. We'll come back to the chemistry later, but this could explain the strong Balmer break. A dense stellar population would explain the brightness. And if these galaxies were packed with dust, as starburst galaxies often are, that would explain the redness too. It was almost all said and done, except for one annoying detail. The maths just didn't work. Researchers soon realized they were running up against two major problems. The first was how much dust they would need. Dust in galaxies comes from one main source, stars. And there's a very well-established relationship between how many stars a galaxy contains and how much dust these stars can produce. In late 2024, Caitlin Casey and her team at the University of Texas in Austin calculated their expected stellar population based on the optical light detected from the little red dots. But once they applied the star-to-dust ratio, their stomachs dropped. Their calculations only yielded 1% of the dust needed to explain the redness they were seeing. And now, a shortfall of 2 orders of magnitude could only mean one of two things. Either the well-established dust formation models are wrong, or the main light source of these little red dots wasn't stars. The second problem was the brightness. To explain the overall brightness of little red dots using just stars, you'd need an impossibly high density of stars in a very compact region of space. They'd only be a few astronomical units apart, but this close together, stars would be colliding and merging all the time, and the gravitational dynamics would be far too unstable. What's more, these little red dots don't look like normal galaxies. Usually we can see some kind of internal structure, but even though James Webb has the highest resolution of any telescope we've ever built, the little red dots just appear as points of light, single dots in the night sky, like stars appear to the naked eye. So either the little red dots are really tiny, or their light is so dominated by a single central source that it drowns out any other surrounding signature that might exist. Which brings us to the second theory. What if little red dots aren't star-filled galaxies at all? What else could explain their properties? Problems like this require sifting through mountains of data. Searching for vital information in all that noise can be worse than finding a needle in a cosmological haystack. It's not a task to be attempted with an Excel spreadsheet. And if you're a scientist or engineer using data to solve problems, why not try something a little more intuitive, like the sponsor of today's video, JUMP. JUMP is a statistical discovery platform perfect for anyone looking for answers in data without the hassle. Right off the shelf and free for anyone in academia, JUMP gives you trusted, powerful data analytic tools, whatever your experience level. You can easily import data, even from massive, messy datasets, and swiftly analyze it dynamically and visually. JUMP helps you cut out the noise and see what really matters. You don't even need a degree in statistics or programming, as JUMP will do all the heavy lifting for you. But if you are a coding aficionado, then JUMP's Python integration still gives you the freedom to work the way you want, but with a team of specialist statisticians at your fingertips. So give yourself more time for the science or engineering you'd rather be doing. Go check out JUMP's webpage by scanning the QR code on screen or by following my link in the description below. Now, speaking of analyzing data, what was the second explanation for those little red dots spotted by the James Webb Space Telescope? Well, at the center of most galaxies, you can find a supermassive black hole surrounded by an accretion disk of gas and dust. As it spirals inward, the gas is compressed and heated to over 12 million degrees Celsius, and it emits a powerful glow. Active black holes are some of the brightest objects in the universe. Could they be behind little red dots? Surrounding the accretion disk of a black hole is a donut-shaped ring of gas called a torus. If you're looking at the torus side on, that dust sits between you and the bright black hole, absorbing shorter wavelengths and letting longer red and infrared ones through. Sound familiar? Little red dots as black holes made sense. It would also explain the brightness, point source morphology, and reddish color. To top it all off, their emissions show broad Balmer lines, which suggests there is a lot of gas spinning at thousands of kilometers per second around something central. Orbiting gas moves both towards and away from us at extreme speeds. The light moving away from us is redshifted, while the light moving towards us is blue-shifted. This exaggerates the spectral lines in each direction, broadening their profile. The faster the orbital velocity of the gas, the wider that broadening becomes. And this is exactly what we would expect from a massive black hole feeding on lots of gas. So far, things were looking good for the black hole theory. That was until researchers noticed something vital was missing. You see, as far as we know, active black holes always emit X-rays from their accretion disks. But when astronomers measured the little red dots, they found no trace of X-rays at all. This was a devastating blow to a promising theory. As if that weren't enough, there was one more problem. The black holes seemed too big for the galaxies they were in. In the local universe, black holes are usually around 0.1% of the mass of the galaxy around them. This is such a consistently observed relationship. We think galaxies and their black holes must co-evolve together, using some kind of feedback loop mechanism that keeps them in tight check with each other. But when researchers started looking at little red dots, they noticed they had much higher black hole to galaxy mass ratios than we're used to, closer to 10%. It was almost as though the black hole had somehow grown to full size before the surrounding galaxy had the chance to catch up. Both the Starburst Galaxy and active black hole theories had their merits, but neither could fully explain what was going on with these little red dots. Astrophysicist Fabio Pacucci at the Harvard Smithsonian Center for Astrophysics explained the dilemma perfectly. If they, little red dots, contain black holes, those black holes are enormous for such small galaxies. But if they only contain stars, the galaxies are too compact to contain all of them, reaching stellar densities that are unthinkable. So if little red dots are not young galaxies of hot stars, and they're not black holes, what could they be? Is it possible we've stumbled upon an entirely new type of cosmic object, one unlike anything we've ever seen before? This was exactly the question Anna de Graaf and her team set out to answer. De Graaf is an astrophysicist at the Center for Astrophysics, Harvard and Smithsonian, with a particular interest in the most extreme objects in the early universe, the things that sit furthest outside the expected distributions. So she designed a survey to go after them directly. The Red Unknowns, Bright Infrared Extragalactic, or RUBIES survey, was a deliberate hunt for the reddest, brightest, rarest objects in the sky. During 2024, DeGraff's team spent nearly 60 hours of web time obtaining spectra for 300 red sources, of which they think 30 to 50 were the mysterious little red dots. This made it the largest ever spectroscopic sample of these dots at its time of publication in March 2025. The objects ranged in age from 650 million to 1.5 billion years after the Big Bang. But while she hoped her survey would bring calm clarity and definitive answers to the field, it did, of course, the exact opposite. RUBIES revealed that these bright red objects are far more diverse than anyone initially imagined. Even though they seemed similar when imaged, spectroscopic data showed they were actually several different types of objects, such as dusty galaxies still forming stars, other galaxies that may have stopped forming stars surprisingly early, and active black holes powering galactic nuclei. It seemed no matter which side of the Starburst Galaxy versus black hole debate you were on, you were, partially, right. But within that sample, there was a subset that didn't fit any of these categories. Objects with the V-shaped spectra, the broad emission lines, the point source morphology, all the signatures that had resisted explanation from the beginning. And then, in July 2024, the team stumbled upon a little red dot 11.9 billion light years away, with a spectrum so extreme it stopped them in their tracks. They called it the cliff. To understand why the cliff was so important, you need to understand what the Balmer breaks we saw earlier are really telling you. Think of electrons around an atom like fixed rungs on a ladder. They can only exist at specific energy levels. When a photon comes along, carrying just the right amount of energy to push an electron up a rung, that photon gets absorbed and the electron gets excited. Every element has a unique electron configuration, so each element absorbs photons at unique wavelengths. This is why spectroscopy works as such a precise fingerprinting tool. For example, for hydrogen, 364.6 nanometers is the critical wavelength. It corresponds to the exact energy required to liberate an electron from the second energy level completely. Longer wavelengths are lower energy, shorter wavelengths are higher energy. So any photon with a wavelength shorter or equal to 364.6 nanometers has enough energy to ionize the hydrogen from that level and will be absorbed. Any photon with a longer wavelength isn't energetic enough to bring about this change. That's why the presence of a Balmer break tells you that there's hydrogen between a light source and your telescope. Usually, a messy, complex object like a galaxy exhibits a smeared, gradual break because stars of different temperatures and densities are sending their light through gases of varying densities. The sharper the break, the more pure the hydrogen atmosphere you're dealing with. But a near vertical break, like the cliff, is twice as strong as that of any ancient cosmic body previously observed, which is why it's so intriguing. The extreme properties of the cliff forced us to go back to the drawing board and come up with entirely new models, DeGraff admitted. It seems this little red dot was sending mixed signals. On one hand, spectra analysis appeared to suggest the object behind the cliff was a supermassive black hole. On the other hand, the dramatic Balmer break indicated a huge amount of relatively homogeneous hydrogen gas around it, like you'd expect of a very young star. Could this be an entirely new type of object? One that was somehow both black hole and star at once? DeGraff thought so. She dubbed the object a black hole star. A black hole star, unsurprisingly, has characteristics of both black holes and stars. They're shrouded in giant spheres of hot, dense gas, which makes them look like the atmospheres of traditional fusion-powered stars. But instead of running on fusion, they're powered by supermassive black holes accreting matter at breakneck speeds, converting it to energy and releasing light as a result. But where does all that hydrogen come from? And if there really was a black hole at the center, why were there no X-rays? Although perhaps the biggest question is, how are they made? The universe seems to be made up of an invisible infrastructure of dark matter, spinning scaffolds called halos. You can think of them as being embedded in an interconnected web, one that looks surprisingly similar to the networks of neurons in your brain. We can't see these scaffolds, but we can map them with gravitational lensing, and they seem to indicate the parts of the universe where galaxies form. Most dark matter halos spin relatively fast, which causes the gas and matter inside them to spread outward, like the swings on a carnival ride stretching further out the faster they spin. But a very small fraction of halos spin extremely slowly. And in those low-spin halos, the gas doesn't spread, it stays dense, compact, and concentrated. We think newborn black hole stars could form in places like these, where enough hydrogen is still present to give us the properties we see in little red dots. As for the missing X-rays, they're not missing at all. They are trapped. In a black hole star, the surrounding hydrogen envelope would be so dense that even high-energy X-rays couldn't punch through it. They would get absorbed by the gas and re-emitted as thermal energy and the red optical light we see instead. Okay, but what about all the other unanswered questions? The strange V-shaped spectral energy distributions, all the missing dust, and the black holes too big for their own galaxies. How does the black hole star tackle these challenges? Lucky for us, astronomer Rohan Naidu of MIT and his team have some ideas. In 2025, they were studying an object they also referred to as a black hole star, and found it to have a thick hydrogen gas envelope about 40 astronomical units wide, plus one of the strongest Balmer breaks ever witnessed at any redshift. Naidu argued the black hole star is a two-component object, a black hole star which produces broad emission lines, a strong Balmer break, point source compactness of light, and strong red emissions, and a star-forming host galaxy that produces narrow emission lines in the UV spectrum. Taken together, this compact object would produce a V-shaped spectral energy distribution just like what we see from little red dots. The low-energy red emissions from the black hole star and high-energy UV emissions from the surrounding host galaxy superimpose to create one unusual spectrum. The object Naidu and his team were studying wasn't a little red dot itself, but by examining it, they concluded that black hole stars, when embedded in brighter host galaxies, produce the little red dot properties we've seen. The remaining issues of dust and overly massive black holes go hand in hand. Under the black hole star model, little red dots wouldn't have any dust at all. They're red due to the opacity and the surrounding dense gas. Since there's no dust to worry about, there's no shortage to account for. And the overmassive black hole problem is also connected to this dense cloud. The standard way to calculate a black hole's mass is to measure how broad its emission lines are. Broader lines mean faster moving gas, which means a more massive black hole. But in a black hole star, photons don't travel cleanly outward. They bounce repeatedly through the thick gas envelope. With every collision, their wavelengths shift slightly. The cumulative effect produces emission lines that appear broader than they should be, leading scientists to overestimate their mass. When researchers corrected for this, the estimated black hole masses dropped by orders of magnitude, bringing them more in line with the expected 0.1% galaxy mass we see in our cosmic neighborhood. Black hole stars sound like something out of science fiction, but they elegantly solve the biggest hurdles we've encountered with the little red dots. And the craziest part of all this is that they were predicted 16 years ago by theoretical astrophysicist Mitchell Begelman from the University of Colorado. In a 2008 paper, Begelman proposed something called quasi-stars. His model described a black hole forming from a stellar remnant or small seed inside a dense gas cloud. Then, rather than the surrounding envelope dispersing, it would stay bound. The black hole sits at the core, feeding, while the outer envelope glows, not from nuclear fusion like a normal star, but purely from the energy of the black hole consuming gas at its center. From the outside, it would look like a single, enormous star, but inside, it's actually a supermassive black hole. Hence, black hole star, or as he called it, a quasi-star. Begelman's model predicted that a black hole in this configuration could grow at extraordinary rates, reaching thousands of solar masses in just a few million years while the envelope slowly cools. Eventually, it hits a temperature floor of around 4,000 Kelvin, and at that point, radiation pressure wins. The envelope gets blown away. The quasi-star phase ends, and what remains is a naked black hole. Begelman argued that rather than a type of object, quasi-stars could be a brief phase, early in a black hole's life, lasting only a few million years. He even suggested that if a black hole were later to encounter another episode of extremely high gas inflow, similar conditions could theoretically arise again, raising the intriguing possibility that some black holes might pass through quasi-star-like phases more than once across their lifetimes. This could explain why the little red dots vanish from sight 1.5 billion years after the Big Bang. Perhaps the perfect conditions for high gas inflow are just not satisfied this late in the universe's lifetime. Could we be confirming observationally what Begelman has already known for close to 2 decades? It probably goes without saying, but despite the black hole star breakthrough, there is still a lot of uncertainty in this field. Papers are being published faster than researchers can read them, with hundreds coming out in just the last 2 years alone. For right now, the black hole star interpretation seems like the best fit to the data we currently have, but it hasn't been confirmed yet. There are still plenty of open questions that the theory doesn't cleanly answer. For instance, how common is the black hole star phase? How long does it typically last? What triggers it? We don't know exactly how the envelope forms or what determines when it disperses. The life cycle of a black hole star, if that's what these objects are, is still unmapped territory. But what makes little red dots genuinely significant, beyond the immediate mystery, is what they might represent in the larger story of how the universe came to look the way it does. One of the deepest unsolved mysteries in astrophysics is the origin of supermassive black holes. We know they exist at the center of almost every large galaxy, including our own. We know some of them were already billions of solar masses just a few 100 million years after the Big Bang, which is just too fast to seem possible. The conventional pathway to black hole formation predicts objects should be about 10 to 100 solar masses by that point in time. The black hole star model offers a potential way out of this paradox, and it works on 2 fronts. Firstly, as we discussed, the broadening we see in the emission lines could be exaggerated due to photon scattering, making the black hole seem more massive than it is by a factor of about 100 to 300. And secondly, supermassive black holes might not be restricted by the speed limit we once thought. See, black holes have a natural ceiling on how fast they can feed, called the Eddington limit. It's set by the pressure of their own radiation pushing back against infalling gas. But dense enough surroundings can push that limit higher than initial predictions suggest. The fact that black hole stars are surrounded by dense hydrogen atmospheres makes them exactly the kind of environment that could allow black holes to bypass their Eddington limit entirely, since the limit shifts from being calculated from the black hole mass alone to being calculated on the entire envelope's mass, which is much larger. The findings surrounding black hole stars indicate supermassive black holes might be smaller than expected and able to grow faster than we thought. a possibility that excites scientists working with their growth models, since it seems to ease the unresolved tension slightly. And an even bigger question is, where did these black holes come from so early in the universe? So far, the only pathway we've directly observed is through stellar collapse, which takes billions of years. But these little red dots already existed 600 million years in, and are far too massive to have grown from stellar mass seeds in that amount of time. So what happened? Well, in theory, massive clouds of primordial gas in the early universe, under the right conditions, could collapse directly into a black hole without ever forming a star at all. These direct collapse black holes are a well-established theoretical concept, but we've never actually seen observational evidence of it. Could the little red dots be the first sightings of such a phenomenon? Only time will tell. For now, the focus of little red dot research is on building out the basics, measuring the temperatures, luminosities, and surface characteristics of little red dots with enough precision to construct something like the life cycle chart we have for ordinary stars. We've never had one for black holes, and little red dots might finally make it possible. Ultimately, science is the pursuit of truth. If one new discovery calls old models into question, it's worth throwing the old playbook out, no matter the mountain of work it creates, if it means getting closer to understanding the true nature of our universe. Thanks for watching. If you've been enjoying Astrum's videos and want to help keep this channel thriving, I want to ask you to take less than a minute to check out the Astrum Patreon. It's not just ad-free videos, but it's a way to make Astrum's videos less reliant on sponsors and algorithms. The link is below. Your membership directly helps ensure that future videos can stay independent, high quality, and consistent, created for curiosity, not clicks. Thanks so much for considering it. I'll see you next time.